light engine size so that people can wear it every day. They're not too heavy, they're comfortable to do. Unfortunately, this is a goal that has not yet been achieved, and it's very, very difficult to do. And we have a new approach how to build a light engine to make this possible. To go again through how it actually works, the display unit of smart glasses always consists of two pieces. One is the waveguide in front of the eye, the other one is the light engine. We built the light engine. It's an LCoS-based light engine, very classical, but we have a different type of illumination, which we call the quantum light chip. It's a laser array, very collimated, very bright. We can turn on and off different laser diodes to segmentize illumination for better energy efficiency. And we have an active despeckler integrated in this illumination unit to get rid of coherence artifacts. This collimated light is illuminating the LCoS. The LCoS has, with the polarization change, generates the image. And in this very classical design, you use then a PBS to reflect out your image through the lens and into combiner to generate your image. Just to give you a bit of an understanding why we are going for this approach, the key thing is that we provide a very well-controlled at-and-do, a very controlled and collimated light emission. The difference is that LED sprays light in all kinds of angles, making it much harder to control. Additionally, the laser light that we use is already polarized. So, and LED light is not polarized, which already makes a factor 2 in terms of energy efficiency. And this means that with this illumination unit that we're building, you can make the light go very smoothly through the engine with very low loss and generate this high brightness, high quality and low energy consumption image that everybody wants to have in their smart glasses. To go a bit more deeper in what we actually do, so as I said, we provide illumination units that are replacing LEDs in current LCoS light engines. And this, what we call the quantum light chip, is what you see on the left in the render. It's a conceptual thing. It's a piece of glass, laser diodes coupled to it from the side that emits this laser ray. And then, of course, we illuminate with this an LCoS, and the LCoS then generates the image. How do we create these laser array? We have a unique waveguide technology in Vienna where we produce these chips, which is direct laser writing. So we take a piece of glass, standard display glass, and we inscribe into it these fiber-like optical waveguides. This allows us to control the flow of light very precisely within the piece of glass, and we can generate then the beam array, which you see conceptually on the right. And this is all powered by standard off-the-shelf laser diodes that are then coupled to this waveguide structure. Going back to what a classical LCoS light engine would look like using our device, this is a very typical LCoS design. I just want to highlight the only thing that we're changing is the bottom part. That's the illumination unit. So you can see examples of this architecture in our booth, just over there. And we can show you how this works. Of course, you can also generate different layouts, PBS 3D layouts, anything you can build with LED, you can also build with our illumination unit. I just want to come back again to the problem statement. How do we get to this 3000 nits and low power consumption that everybody wants to see from the smart glass display unit? To give you an understanding, there are different kinds of combiners. For example, 30-degree and 50-degree are standards in the market. And of course, if you increase your field of view, you're going to need more lights, right? It's different. It's higher amounts of photons coming from higher fields of view that coming towards the eye. So you have to generate all these photons. So to achieve the 3000 nits with a 30-degree combiner, you're going to need already 3 to 4 lumens, which is quite challenging for most of today's projector technology. If you want to go to 50-degree, that gets even more challenging because you're then around 7, 8, 9 lumens of light that you have to provide. So this is one part. The other part, as I said, of the display stack, so to say, is the light engine. That's what we are doing. And also this is a metric, right? Because if you now have to produce 5 lumens, how many milliwatts of electrical power do I need to generate these 5 lumens? And this is then the power curve of our light engines, which has one added detail, and that is that we can locally dim the illumination, as I said before, to lower the amount of energy needed, because almost all AR scenarios use very small amounts of pixels. right? It's just navigation, it's just small symbols, so you don't gonna have all the pixels on all the time. So if you have 15% of the pixels on average, you can tailor your illumination unit to use less power. So if you use this approach, and now you want to figure out, if I build a smart glass with this new technology, what kind of power consumption gonna have? And always we're aiming at 3000 nits, because this is gonna be the level which is bright enough to see it also outdoors. So if we want to have like the 3.5, 4 lumen that is necessary for a 30-degree field of combiner, we can end up with around 200 to 300 milliwatts of average power consumption of the light engine. And this is of course in the very high brightness scenario. If you're indoors, this is gonna be less. For the 50-degree field of view, of course it's gonna go higher, but the power consumption is still gonna be below half a watt, which we think is the critical threshold which you should not exceed, even temporarily in smart glasses per eye. One thing I want to highlight is that what we can do is localized illumination of the LCoS, and this is going to be also key to achieve lower power consumption. Because otherwise you're going to illuminate a lot of pixels from the LCoS that don't actually need any light because they're dark. Our current demo that you can see over there has 2 zones, but we want to expand it first to 4 and then later to 9 zones. To give you an idea what we're planning to do, so what you can see at our booth are R&D prototypes. But we're now going to iterate very quickly on this in the next few months. And we want to launch 2 different series of products to the market. The first going to be the Fusion. This is going to be as quickly as possible to the market without doing too much development effort. So rather bulky, but very luminous, high field of view. This is aimed at enterprise customers. They're very desperate to find a solution. And then later on, we want to launch a pico ray, which is like the real effort and the real goal of this technology, going much, much smaller, even higher in efficiency, and this is then aimed at consumer smart glasses. And with this, I would like to end and invite you over to our booth, which is like 50 meters from here. Thank you.